So in order for us to do this, or raise our hand, grab a cup of coffee, whatever it is, jump, we need to initiate the movement. So the movement might start up in our brain. We might decide that we want to move. So that comes from this familiar guy up here. This is called our cell body of our neuron, and it can come from the brain or it can come from the spinal cord. So we all know that after the cell body, we have an area of the neuron called the axon hillock, right?
Who comes up with these terms?
I don't know. Hillock, yeah, I don't know what that means, but anyway.
They must be nerds.
This is the axon hillock. And that is where the action potential is generated. So we have the idea to move, and then the action potential comes from the axon hillock. Yeah, so then the action potential travels down the axon of the neuron. And where does it go, you might be wondering?
I have no idea. Are you going to show me?
I will.
Okay.
So then the neuron actually branches off into terminal ends with these cool little synaptic knobs on the end of them.
It looks like feet.
It does. Little feet. Little neuronal feet.
Okay.
So this is essentially our nerve. So we've got our axon hillock, action potential coming down, and it branches off into the synaptic terminal. And we've got the synaptic knobs down here. So we know that the synaptic knobs can attach to many things. It can attach to a gland cell, it can attach to a muscle cell, it can attach to another neuron. So in this case, let's talk about a muscle cell, because that's really what we're wondering, right? How does this cause a muscle contraction if this is a muscle belly? Right?
Right.
Okay. So let's zoom in. So we're going to take this little guy here and blow it up and talk about what's going on.
Okay.
At the synaptic knob.
Okay.
Okay? All right. So if we've got our synaptic knob, and we know it joins up with the muscle fiber, this whole set here is called the neuromuscular junction.
Hold on, Janet. So just to be clear,
Yeah.
this is this.
Yes.
So this is like a Bigfoot.
This is like, yes,
Okay.
a Bigfoot.
I got you.
Blown up. Expanded. Just blows your mind.
Okay, so we're zooming in.
We're
this
zooming
is like
in.
real
Yeah.
microscopic. I got you.
Yeah. So at the synaptic knob, we've got the action potential coming down the neuron. And what happens as a result of that action potential coming down the neuron, we have calcium just hanging out outside the synaptic knob.
Like calcium from like milk calcium?
Yeah, calcium from like milk calcium.
Oh.
So calcium will come through voltage-gated channels. And what that calcium does is it allows these vesicles that are hanging out in the synaptic knob that are full of little blobs of acetylcholine, which is our excitatory neurotransmitter. Calcium will cause these guys to be released to the muscle.
Oh.
Cool, eh?
How does that happen? What happens next? Tell me more.
Okay, I will. So we have calcium coming in, these synaptic vesicles releasing acetylcholine, and what color am I on here? Yellow. So acetylcholine will come out through exocytosis into the synaptic cleft, and a really cool thing happens. It actually binds to a receptor on the cell surface.
I'm beginning to realize why students don't raise their hand more often. But go
Why?
on.
Is this confusing?
Well, no, it's complicated, but
It is.
it's making a lot more sense as you draw it.
Good. So acetylcholine will bind to the acetylcholine receptor. And what that does is cause the receptor to open up. And remember our friend sodium? We learned all about sodium back in phys. Sodium will come into the cell once acetylcholine binds the receptor. So I'll just put my little acetylcholines on here. So that's how the action potential travels down the nerve to the muscle fiber. And then at the motor end plate, we've got sodium coming into the cell. And then
So this is the part I was
contraction might
confused
start.
about. Do
Yeah.
you know how contraction actually happens, though?
No, but maybe you can tell me.
For some reason, that's the only part that I understand. So sure, I can show
Okay.
you what happens next. We'll just pick it up from when the signal has gone from the neuron.
Yeah.
Now it's inside the muscle, right?
Yeah.
So let's just pretend this pink represents the signals inside now, right?
Okay.
And you have this weird structure.
Mm-hmm.
May I borrow the blue?
Yeah.
Because blue's cool.
Blue is cool.
It kind of looks like a spider web-ish looking kind of thing.
What is this spider web
They,
looking thing?
They call it the sarcoplasmic reticulum. I'll just put SR.
Okay.
Janet, I don't know who comes up with these words, but it is what it is. Inside here
Yeah.
is also lots and lots of this calcium.
There's that calcium again.
Yeah.
So weird.
So what happens is once the signal is inside, this signal is actually telling this SR, hey, calcium, it's time to get released.
Okay.
So now you have this calcium just all over the muscle cell.
Yeah.
So let's just zoom in to just, if we were to pretend that we're zooming into this area right here and to kind of blow it up.
Yeah. Let's blow it up over here.
Sure. Let's do that.
Yeah.
Here's what it looks like if you were to zoom into one kind of like structural contractile unit of a muscle cell. There's
What's that
two
called?
parts to it. It's called a sarcomere.
Sarcomere. Cool.
Yeah, we'll get to that later, but let me
Okay.
just draw you what it would kind of look like under a very strong microscope.
Okay.
There's a thin part.
Yeah.
We'll call this the thin filament.
That has another name, doesn't it?
Yeah, they also call it actin
Cool.
because scientists just like to have lots of terms for the same thing. That way it causes more confusion.
Oh yeah. Students love that.
But see, the thin has actin, and it also has another part that kind of looks like a rope. They call this one tropomyosin.
Again, a weird name.
I know. And there's actually one last part on this. Put a different color. It's on top here. This is called troponin.
Troponin.
It's just another term. They all sound the same, but they're all different structures.
Right.
So that's the thin part. Then there's a thick part. If there's a thin, there's got to be a thick. So there's a thicker part. And this one has heads on it. It sounds weird, but these are actually called myosin heads.
Okay.
Myosin heads.
So where does this
So this is
calcium
the
come
thick.
into play?
The calcium, well, I'm going to tell you.
I wanna get
where
back to
you
the
went.
calcium.
You know,
I
it's
like the
coming. It's
calcium.
coming back. So if we were over here, the signal came down,
Yeah.
told this sarcoplasmic reticulum to release calcium.
Yeah.
Then we took a trip across the board, or the cell. And then what happens is, what color was calcium? It's blue, let's keep blue.
Yeah.
Calcium's looking for this spot here,
Yeah.
one of these troponins.
Troponin. Yeah.
So what happens is when calcium is stuck here,
Yeah.
it's moving this tropomyosin part out of the way.
Okay.
And what that's allowing is for this thicker filament part, the myosin head, to attach. Once this thick filament, the myosin head, comes into contact with actin and they are in contact,
Yeah.
that is muscle force production.
It's a full contact
It's called
sport.
a cross bridge.
Yeah.
It's called a cross bridge.
Cross bridge. Okay.
When myosin's in contact with actin, it forms a bridge. They're in contact.
Okay.
The more of these cross bridges you have, the stronger the contraction.
I always wondered that. That's what keeps me up at night.
No way.
Yeah. Wait.